So you've seen antiderivatives by this point, and you've seen how to do integrals and how to do integrals of polynomials, trig functions, exponential functions, and so on. But what if you get a really tricky one? What if you're asked to evaluate integral of x e to the x squared? Something you would not really know off the top of your head how to do. Well, we can't use our standard polynomial tricks or any of the other small tricks we've learned because they won't work here. Integrals are much more difficult than derivatives because there's no set rules for everything. So we need to develop a new technique of integration. So let's look at something real quick before we figure out how we can do this. So the trick we're going to use is basically a change of variables. So what we're going to do, instead of integrating with respect to x, we're going to change our variables to make this a little easier. So how can we do that? The way we do that is we look for a function next to its derivative. So why would we do this? Well, if we say, well, we have a function here, x squared, that kind of looks like its derivative right there, just off by a constant. So let's call this function u. Okay? Well, this doesn't look helpful, but if we look at the derivative of u, that's 2x. Well, what we can do is use our chain rule again here. We can say that du is 2x dx. Now, why should that be true? What is happening here? Well, you can think of it one way, as if we're just treating this as a fraction. You can say, well, we have a du dx, so let's just move dx to the other side. Or you can remember by the chain rule, du dx dx is equal to du, which is exactly what we've done here. So what's happening is we're changing our variable from x's to u's. But we have to change the dx as well, because we'll be no longer integrating with respect to x. We want to integrate with respect to u. So this is helpful because in our problem, we have an x dx. And now we've regained that x dx. So if we want just that, we can say 1/2 du is x dx. So we can say this is really the integral of, well, x dx is 1/2 du, and e to the x squared is now e to the u. That's a really simple integral to solve, because that's just half of the integral e to the u to u. Remember, it doesn't matter what we're integrating with respect to when we actually do our antiderivative, it's still going to give us e to the u plus a constant. Now we can substitute back in our u and say this is 1/2 e to the x squared plus c. So we've done a change of variables. We call this a U substitution because we're substituting U in for our x, and that's the name of this technique of integration. Now when you do this, be very careful because you always have to have something like this. You need to transform your dx into a du. Don't forget that. Don't end up writing something like 1/2 e to the u. You always have to have a du here. Okay? If not, you might miss this constant, or at the very least, you'll be taking off points on your test or homework if you forget that. So let's look at another one. Let's say we want to find the integral of sine of x cosine of x. Okay, so here's one of the tricky parts with U substitution. There are multiple substitutions that will work for any given integral. So if we look at this, we say, oh, well, here's sine, whose derivative is cosine. But we could also say, oh, look, there's cosine, whose derivative is sine. So we could really pick either one to be our U substitution. But for now, let's just pick U equals sine of x. So we found a function right here near its derivative, right? So du dx is cosine of x, which means that du is cosine of x dx. So now we see that we have this cosine of x here, so we can substitute it in. So our integral becomes the integral of u du, which of course we know how to solve. It's 1/2 u squared plus a constant. So this becomes 1/2 sine squared of x plus a constant. Now let's see what happens should we do it using cosine as our substitution. So we'll have u equals cosine of x, which means that du dx is minus sine of x. So du is equal to minus sine of x dx. So we can bring the minus sign over to get a sine of x dx here. So we have minus du equals sine of x dx. Okay, so now let's do our integral. So now we have an integral of minus u to u, because we have a minus sign from the minus du. Okay, well again, that gives us 1/2 u squared plus a constant. Okay, so now that we have negative 1/2 u squared plus c, we can plug back in our u, and so we get minus 1/2 cosine squared of x plus c. So it may look like we have the wrong answer, because we have a cosine function here and a sine function here. But these are actually both correct answers. And the magic that this may seem like comes from the constant. So even though we have different functions, we have a constant to offset them, because cosine squared and sine squared are really only off by a constant. Is sine squared plus cosine squared is 1. So if you were to actually do a definite integral, say from pi to 2 pi, you would get the same answer, even though you have different functions. So it doesn't matter what you pick for u, even though it may look different at first, you will actually get the same answer both times. So don't freak out if you're doing a problem and your friend got a slightly different answer. You may have picked a different u, and that's okay. So before we get to these definite integrals, which can have different functions but end up being the same, let's do one more indefinite integral to really show another example of this. So let's do integral of natural log of x over x dx. So it may not seem like at first that we even have a function here as derivative, because we have natural log of x divided by x. But we can rewrite that as 1 over x times natural log of x. So we have a natural log next to a 1 over x. That's its derivative. So we set the function equal to u, and we calculate its derivative. Now we know that du is 1 over x dx, which we have right here. So we can say that this integral is really u dx, which is 1 over x dx is du. So we just have the integral of u du. Again, that is just 1/2 u squared plus a constant, which is 1/2 natural log of x squared plus constant. Okay. So now that we've seen these examples of definite integrals, let's move on to now that we've seen the indefinite integrals, let's move on to definite integrals to see exactly how these work with U substitution. Okay, so now let's look at our definite integrals. So let's return to our first one we did, which was x e to the x squared dx. Well, now we're going to evaluate it from 0 to 2. So recall that what we did the first time was we said u equals x squared, therefore 1/2 du equal x dx, which meant that this was really integral 1/2 e to the u to u, which was 1/2 e to the u, which was 1/2 e to the x squared. So we have to substitute this back in, and then we can evaluate, which gives us 1/2 e to the 2 squared, which is e to the 4, minus e to the 0, which is 1. So that takes a while. We have to do a u substitution, then evaluate the u, and then plug back in our x, and then plug in our x values. But what we can actually do is we can skip this whole step of plugging back in our x. So what we want to do is say, well, when we're looking at this integral, so let's break this down. 0 to 2 of x e to the x squared. What are we saying here? We're really saying we're integrating from x equals 0 to x equals 2. Well, when we want to rewrite this in terms of u's, we want to integrate over all the u values these correspond to. But we know this. We know that u is x squared. So we have our lower bound is at x equals 0, so that's u equals 0 squared. Our top bound is x equals 2, so we have u equals 2 squared, or 4. So when we do this, we no longer have to substitute back in our x values. We can just do this as if it was an integral over u. So we can write this as 1/2 e to the u from 0 to 4, which is 1/2 times e to the 4 minus e to the 0, which is 1, which is exactly the same answer we get. So instead of actually having to rewrite all the x and all this, we can just evaluate it here. So let's do another example of this where we're changing our bounds for u's. So again, let's go back to one of our examples. Let's do the integral from 0 to pi over 2 sine of x cosine of x dx. Okay. So let's go back to our familiar u substitution. U equals sine of x. So du was, you say du dx was cosine of x, which means that du is cosine x dx. So we get the integral of u du. We have our u, then we have our du. Okay, well, now we want to change our bounds. We know u equals sine of x. So again, we're saying this is x equals 0. We're saying this is x equals pi over 2. So we just plug in this value. So we have our lower bound is sine of 0, which is 0. And our upper bound is sine of pi over 2, which is 1. So we're integrating u from 0 to 1. There's no need to plug in cosines and sines back in the answer. So we just get 1/2 u squared from 0 to 1, which is just a half. It's as simple as that. We just change our bounds for u, and we no longer have to do all this gymnastics of switching back and forth between x and y. And this becomes really useful when doing really long problems where u becomes very nasty. So this is how u substitution can really help your life. Okay, so now we're going to do one more example of an indefinite integral using u substitution. So this example comes up time and time again, especially if you're a University of Kentucky student taking Math 113. And this example is something that looks like the integral of 1 over, let's say, 4 plus x squared dx. Okay, so why is this so difficult? Why does this always give students trouble? Well, the reason is this kind of looks like it should be an arctangent, because remember, the derivative of the inverse tangent of x is 1 over 1 plus x squared. So this kind of looks like that. However, we have a 4 here. So what do we do with that? Well, in order to do this, we really want there to be a 1 right here. So the way we get around this is we say this is really 1 over, let's factor out a 4, so that's a 1 plus x squared over 4 dx. So let's simplify this a little further. We can bring the 1/4 outside the integral. 1 over 1 plus, well, if you look at this, we have an x squared over 4. That is the same as x over 2 quantity squared. So now we have something that looks a little more reasonable. We have 1 over 1 plus something squared. So this something we're going to call u. So we're going to say u equals x over 2. So we have du is 1/2 dx. If you just take the derivative and move the dx over. So we have 2 du is dx. So let's write this as 1/4 integral of 1 over 1 plus u squared times 2 du. So this 2 will cancel with that to make that a 2. So we have 1/2 integral 1 over 1 plus u squared du. And now we can recognize this as the inverse tangent of u by this rule. So this is 1/2 inverse tangent of u plus a constant. And then we just substitute back in our u. So this is 1/2 inverse tangent of x over 2 plus a constant. So you have to be really careful when you're doing these, because you have to be careful with these constants and then making a U substitution. There's a lot of steps that involve these, but these do come up quite often, and they're very useful to figure out.